When a source of sound is at rest, its waves behave in a fairly simple manner. This animation shows the waves coming from a still source at even intervals. Sound waves moving away from a source alternate between crests and troughs. This graph illustrates sound wave frequency change as a function of speed. As you can see on the left side of the graph, the frequency is reduced, while on the right side it increases dramatically as the speed of the source approaches the speed of sound. Now I will introduce the Doppler Shift equation to explain this phenomenon. The frequency of the sound waves as it appears to the observer is equal to 1 over 1 plus or minus the velocity of the source divided by the speed of sound, all multiplied by the actual frequency of the sound being produced. In our case, the speed of sound is 340 meters per second at a temperature of about 15 degrees Celsius moving through air. For the source of sound that is at rest given a velocity of 0, the observed frequency of sound waves is simply 1 times the actual frequency of the source. Things become more interesting when a source of sound is moving. Notice how on the left the wavelength decreases while on the right it increases. This causes a change in pitch for the observer. Here's our graph again with arrows emphasizing plus or minus 200 meters per second. Using the same Doppler equation from before, we can calculate the change in frequency for a source moving at 200 meters per second. Going away, the result is 63% of the original frequency, and coming towards an observer, the change is 2.4 times the source frequency. Here's how fast a bike would move around a quarter-mile track at 200 meters per second. Immediately afterward, you will see a bike traverse 100 meters at 200 meters per second.